All right, let me get back to my lecture. Okay. Okay, so let's discuss the concepts of force and mass. So the simple definition for a force is a push or a pull. When you when you put a force on something, that's literally what you're doing. You're pushing it or you're pulling it. Even if you're lifting it, that's still a push or a pull. So there are contact forces, which means that you actually have to be in contact, physical contact with the object. If I push your book, I've got to touch the book and push it. But there are also action at a distance forces that do not require contact. And of course, we already studied one of those in the last chapter when we discussed gravity. In other words, if I have an object, I let it go, gravity on its own is a force that pulls that object toward the center of the earth. And later, I think in the next half of this text, which is Physics 2, you will learn about the electrical forces, which are also distance, action at a distance forces. Okay, so again, because force is a vector, it has both magnitude and direction, we have to use these arrows. So this top arrow simply means I have a force. This represents 15 newtons and it's pointed in the east, due east. Whereas this force is pointed north of east, has a magnitude of 5 newtons. So the first thing we're pointing out right here is that force is a vector. Now, what is mass? Mass is a measure of the amount of stuff contained in the object. In other words, how much matter there is, how much of it is. Mass is not the weight. Actually, weight, we're going to learn, is a force. So what does Newton's first law says? An object continues in a state of rest or in a state of motion at a constant speed along a straight line unless compelled to change that state by a net force. This is Newton's first law. And his first law simply says if an object is moving, it will keep moving. Not just keep moving, it will keep moving in a straight line. Or if the object is at rest, it will remain at rest. Nothing will change unless a net force acts on that object. And the net force is the vector sum of all the forces acting on the object. So if you look around, you probably already see some examples of forces. When you see something hanging like a chandelier, hanging from the top of the ceiling, there's some force that's holding it up. Nails, screws, wires, something is holding it up. If it wasn't, of course, it would fall down. So there's a vector sum of all the forces acting on the object. So here we have a picture of, and on to the left, we have two individual forces. There's a force that's acting to the right that is 10 newtons. There's an opposing force acting to the left that's 4 newtons. And therefore my net force is 6 newtons acting to the right. So the net force on an object is the vector sum of all the forces acting on that object. I haven't explained this term yet, but we will learn that the unit of force is the Newton, and we'll derive that unit soon. So we also learn what happens when a force has components, or in this case, as you can see, these two forces are acting perpendicular to each other. One is going directly north, others going directly east, and therefore we have a net force. Do you think that if this is 3 and this is 4 and this is 5, that this is correct right here? 64 degrees. Can that be correct, class, from what we have learned? Yes or no? Can this angle be 64 degrees, yes or no? Okay, very good, Keston. Because we know a 3, 4, 5 triangle has 2 angles. One measures 53.1, the other measures 36.9. So I'm not sure what they're supposed to represent, unless this is not the net force from these forces. Because if we were to solve this problem, oops, let me go back. We were to solve this problem with this being 64 degrees and this being my opposite side, then we would say that the sine of 64 is going to be opposite over hypotenuse, which is 5 newtons. So my opposite side, okay, the sine of 64, what is that? The sine of 64 is 0.89, and multiply that by 5, and we will get 4.49. So we do that, we get 4.49 newtons. So clearly, this is not the net force for these individual forces. I'm not sure if you made an error there or what. Okay. Now, what is inertia? Inertia is the natural tendency, means it occurs in nature, of an object to remain at rest or in motion. So when an object is in its natural state, that's its state of inertia. And of course, we need to have an outside net force to overcome that. So the mass of an object is a quantitative measure of the inertia. In other words, every object has mass. If it's an object, it has mass. So overcoming its tendency to either remain at rest or how it's moving has to be acted on by some outside force. Now, this simply means that the laws that Newton has written for us to follow, these 3 laws, they're only valid in an inertial reference frame. And all accelerating reference frames are non-inertial. So in our system of discussion here, here on the Earth, all of these laws are valid. So let's look at our notation. The first thing we see here is that we have this Greek symbol, omega, uppercase omega, okay? And what does it stand for? I'm sorry, I'm talking about omega. Sigma. Is this Greek letter called sigma, class? Yeah, I think it's called sigma. And sigma is the symbol that we use for sum. The Greek letter sigma denotes the vector sum. Okay, so we write that. Sigma means I'm going to add up all the forces. The first force plus the second force plus the third force. So sigma is the Greek letter that simply means the vector sum. Now, all of these are vectors, which means all of these have both magnitude and direction. And we've already learned in chapter 2, and what we learned in chapter 1, how to find the components of these vectors. So even though they're vectors, they have components, and we have to use what we've learned already. The beauty about physics is that it builds. So we're going to see now that everything we have learned in the previous 3 chapters will be used now. The author knew that it was best to build a foundation before we introduce the motion or Newton's laws of motion. So what I want to say is, already we've discussed objects moving, but now we know that objects do not just move on their own. There has to be some outside force. When we say the ball was thrown, the ball was kicked, in our last chapter, when we said the football was kicked, well, the person kicking the football, that's what applied the force that sent the ball sailing through the air. So now we have all of the tools we need to be able to clearly define and understand forces. Okay, now let's discuss Newton's second law. When a net external force acts on an object of mass m, the acceleration that results is directly proportional to the net force. So that means that as I increase my acceleration, I increase my force. They are directly related. And has a magnitude that is inversely proportional to the mass. That means if my object gets smaller for the same acceleration, the object gets smaller, or as I keep the force, I say for the same force, if the object gets smaller, the acceleration gets greater. So when it says directly proportional, that tells me as A gets bigger, F gets bigger. Indirectly proportional, as A gets bigger, M must get smaller if F remains constant. So that equation written linearly, written in a straight line, is here. The net force, meaning the sum of all the forces, equals the mass times the acceleration. Now, this is why I wanted you to learn all of your kinematic equations. And that's because this acceleration is actually the same value we would solve for in previous chapters, in chapters 2 and 3. And you'll see that soon. Now, what is the unit? The combination of kilogram, which is mass, times meters per second square, which is acceleration, is a kilogram meter per second squared, and we call that combination the Newton, and we use the symbol uppercase N, the unit of force. Now, there are other units of force. In the SI system, we have the Newton. We also have the CGS system. That stands for centimeter, grams, seconds. So in that system, it's called the dyne. You may have heard of the D-Y-N-E, the dyne. That's a unit of force, mostly in the laboratory, where we have smaller quantities that we're working with, like the centimeter. And our speed is in centimeters per second. The acceleration is in centimeters per second squared. Then we have the British, and sometimes this is called the US customary system unit that we use here in the US. And the mass is in slugs. I'm not sure why it has that U. The word is slug. And acceleration is foot per second squared. Wow, he's got a lot of misspelled words here. He got food. Can you believe that? Food per second squared. Okay. This class is supposed to be the word foot per second squared. And that is the acceleration. Rather than saying meters per second squared, we're saying foot per second squared. And that combination is called a pound. So we have the slug foot per second squared, and that's a pound. That's the unit of force in the U.S. customary system unit. So here we have our first example. What the author wants to show you on this, and this is so useful. This is a useful tool. It's called a free body diagram. Everything has a name so that we can refer to it. But simply what it means is on your XY axis, you identify the forces. Here in the center, this will always represent the object. And then these arrows simply are showing the magnitude and direction of the forces. So here we have a car. So this little dot right here, class, that's my car. Then we have the two guys pushing. So one is pushing with the force of 275 newtons, and the other is pushing with a force of 395 newtons. But there's an opposing force. You will learn later, this is the frictional force. It's the contact force between the car and the surface, which is really a normal force, but we will look at that later. It's the frictional force, which is a component of the normal force. So anyway, we have the sum of these forces moving in the positive direction, and this is my opposing force. So this free body diagram is just a useful way to identify the forces acting on the object. So what's the net force? The net force then is the two forces acting in the positive direction minus, because this force is an opposing force, and we get a net force of 110 newtons. You notice that it is directed along the x-axis. In other words, the net force is also directed in the same direction as the vector force, as the object is moving. So if it's enough force to overcome this force, the object will move in this direction. So where is the acceleration? Well, if it was at rest and now it has some velocity because it had to move, that of course is my acceleration. So my force then, if I knew the mass of this car, I could tell you what the acceleration is. Okay, so if the mass of the car was 1,850 kilograms, then by Newton's second law, this object is moving at 0.059 meters per second squared. So you notice then that my Newton, I'm only doing the units, my Newton is a kilogram meter per second squared, and divide that by kilograms. When that cancels out, then I have the units of acceleration. Now, the components. The direction of force and acceleration vectors can be taken into account by using the x and y components. And we also have learned already that we have motion in the y and motion in the x. So the force vector is equal to, now you notice these are bold because these refer to vectors. These are not bold because these refer to scalars. So it's equivalent to the force on the y-axis and the force on the x-axis. So here we have an example. If you have your textbook, you can look at this first example that we have here. It says a man is stranded on a raft. the mass of the raft and the man is 1,300 kilograms. By paddling, he causes an average force P. So he's paddling. This average force P is 17 newtons and is directed, as you can see here, due east. Now, the wind also exerts a force A. So this force A is the wind blowing on the raft. And this force has a magnitude of 15 newtons and points 67 degrees north of east. Ignoring any air resistance from the water, ignoring all that, find the X and Y components of the raft's acceleration. So now, in order for me to find the X and Y components of the acceleration, I'm going to, as he's done here, draw a free body diagram so that I can see clearly that this force, the force on the air, has a component along the Y and along the X. So therefore, in the X direction, I'm going to have two forces, one from the man paddling and the component of air or the wind along the X direction. And I'm going to have a component from the air along the positive Y direction. So now I need to find out, it says the X and Y components of the raft's acceleration. So the force, the paddling, the P force only is on the X direction, nothing along the Y. Along the force for A has both an X component and a Y component. So now we have, when it's in the traditional method, we know now, we've done this many times, we take the cosine of the angle times the hypotenuse, that gives us the X. The sine of the angle times the hypotenuse gives us a Y. This is what we have firmly learned. So now I know the X component of the force, and I know the Y component of the force. And now once I know the mass, the paddle, the raft, I mean, only has one mass, now I can find the force along the X and the force along the Y. So that's what I do. Once I have found the force along the X, I can find the acceleration along the X, and the same for the Y. Now, what if I wanted to find the acceleration of the paddle, of the raft? The acceleration then, this is my vector A, would be AX plus AY. But we know already that I have X and I have Y. So then, well, in this case, I'll say Y. This is my Y. This is my X. So of course we know that I'm talking about this A. I can't just add them together like I would regular numbers. They cannot add together because one's along the X and one's along the Y. And we've already learned that. That's why I said it's so important that you have a good grasp of what we've already learned about components before we can even begin to understand how this is done. So we've learned that already. Newton's third law. Whenever one body exerts a force on a second body, the second body exerts an oppositely directed force of equal magnitude on the first body. And you may have heard this as equal and opposite reactions, equal and opposite forces. So here we have, suppose that the magnitude of the force is 36 newtons. If the mass of the spacecraft is given and the mass of the astronaut is given, what are the accelerations? So now that means then that the acceleration for each one would be the net force divided by what? The mass of each one. So what are the accelerations? In other words, one's accelerating differently from the other because even though the force is equal, the masses are not. So the spacecraft had a force of 36 newtons and this huge mass, 11,000 kilograms. So it's accelerating at 0.0033 meters per second squared. Whereas the astronaut with this small mass is accelerating in the opposite direction, negative, at 0.39 meters per second squared. But the forces are equal, but opposite. And not only that, they're acting on different quantities, different masses. The force in the positive direction is acting on the spacecraft. The force in the negative direction is acting on the astronaut. Okay, in nature, there are two types of forces. We call them fundamental and non-fundamental. And the fundamental forces that we're going to discuss in this chapter is the gravitational force. But there are also strong nuclear forces and electroweak forces, and these you will cover in the second half of physics. So our force is a fundamental force, meaning that these forces, all of these occur in nature. We do nothing on our own to create these forces. They're just there. And we learn how to use them. On the other hand, there are forces that man creates, and these are non-fundamental forces like friction, tension, normal or support forces. Those are examples of non-fundamental forces. Now, our next law is Newton's law of universal gravitation. Every particle in the universe exerts an attractive force on every other particle. Now that's hard for us to believe because these forces are so infinitesimally small, we don't even know that they're there. But on the macroscopic levels, is where we can see their usefulness. A particle is a piece of matter small enough in size to be regarded as a mathematical point. The force that each exerts on the other is directed along the line joining the particles. So here we have Newton's law of gravitation, the gravitational force. So this gravitational force is equal to the gravitational constant. I call this big G. So now we're going to have another constant that we know that we're going to learn. I call this little g. Little g is 9.8 meters per second squared. I call that little g. I call this big G. And big G is a very, very small number, but its value is 6.673 times 10 to the minus 11. And the units for big G is all of this. Newton meter square per kilogram square. So here we have a particle of mass 1, a particle of mass 2. This force is acting to the right. This force is acting to the left. They are separated by a distance r. And if I want to find the magnitude of this force, remember I said magnitude means it's a scalar. I would just simply multiply big G times M1 times M2 get that product, and divide it by the distance between them squared. Now this distance between them now in this equation is called R, but R simply means the distance from center to center. So we have an example. Here we have mass 1, that's 12 kilograms, and mass 2, 25 kilograms. The distance between them is 1.2 meters, and we asked to find the force. So we simply substitute in these values to this equation, and we solve it. We notice here that kilogram times kilogram, that's kilogram square, that cancels out. And meter square will cancel out meter square. We square 1.2, divide that into 12 times 25. If you do it on your calculator, you get that product, and then you multiply that by 6.67 times 10 to the minus 11, and you get this answer. I encourage you to work this problem out on your own so that you can see how the exponent's changing and how we have to write it in scientific notation with 2 significant digits, because we were given 2 in our given. So this is called the gravitational force. I will be sending you, I meant to do it before class, I'll be sending you the next equation quiz, and that equation quiz will allow you to write all these equations on another sheet. So here we have an example of the attractive force between the moon and the earth. And again, the forces are equal and opposite, and the distance between them here is a constant in this case. So what is weight? The weight of an object on or above the earth is the gravitational force that the earth exerts on the object. So in other words, if I wanted to find the weight of something, I can complete this equation because it says it's the gravitational force between them. But I also can use a different definition to find, or a different equation to find the weight. Now, the weight always acts downward toward the center of the earth. On or above another astronomical body, the weight is the gravitational force on the object by that body. And that's why we know that objects have different weights, the same mass, but different weights out in space, say on the moon or on some distant planet. Okay, class, what time is it? Let me take a 5-minute break while I try to pull up the equation quiz. So take a 5-minute break. I'm going to look for the equation quiz real quickly. Okay, class, I have returned. And unfortunately, when I'm in my Zoom class, I cannot send you the information that I just was pulling up, but I'm going to share it with you very quickly. Okay, so what I have for you here is the comprehensive review, chapters 1 through 4, that I want you to complete to use for the midterm exam. So I tried to arrange everything that you will need that we've learned so far, what we're learning now, in one file called the comprehensive review. So if you notice here, I have the conversions that you'll need to be able to use. And we'll fill out some of this now that I haven't gone over. So we just discussed that mass and weight are not the same thing. But we do know that every mass has weight. So the mass of 1 kilogram corresponds to 2.205 pounds. You can fill this out later. If I put a 1 kilogram mass, say on an English scale, the weight of it would be 2.205 pounds. Then this 8 through 10, we already know. Now we have learned that a kilogram meter per second square, we call that a Newton. And this is the SI unit for force. And we're also going to learn that is the SI unit for weight, because weight is a force. Then we learned that a slug foot per second squared is called a pound. And this is the British Empire or the US customary system unit, also for force and also for weight. Now, what about our constants? We have our constants. Okay, so I'm going to, now this is being recorded, so I will send this to you as soon as I have it ready to send out to place it on YouTube. So I'm going to clear this for a minute so I can move this up. So here, we already know the value for acceleration due to gravity. That value is 9.8 meters per second squared in the SI system and 32 feet per second squared in the British Empire or English units. The new thing we have learned now is the universal gravitational constant. So here we call this little g. We're going to call this big G. And we said that is 6.67 times 10 to the minus 11. The units are Newton meter square per kilogram square. Now, again, I will send this sheet to you as soon as we end our lecture. I'm going to send this sheet, this comprehensive quiz to you so you can fill these numbers out. Once you print and use this, this will become your study guide along with everything else we have learned for the exam. Now the equations here at the bottom are the same equations we've already learned, and we're going to add some new ones now. So let's go to the first one we've already learned. Okay, so number 21 is the first equation that we have learned today. So that equation we said was writing it linearly. The net force, which is a vector, is equal to ma. And the unit is newtons. The other equation we learned today is 23, the gravitational force. And that force, we said the magnitude of it is big G times the mass of the first object, mass of the second object, all divided by the radius squared. Radius meaning the distance between them. So this force can be in newtons or it could be in pounds. British Empire, pounds. Okay, so that's some of the things we have learned so far. So now we've learned this, let's put a little bit of this into practice as we solve some of these homework problems. So I'm going to show you the homework that I'll be sending also. Okay, so here we have our homework. This will come in your email as soon as I end today's lecture. So use the notes, use your textbook, use your lecture notes to answer these questions. But let's go down to a problem just for me to show you how easy these problems are. So it says, when the net force that acts on a hockey puck is 12 newtons, the puck accelerates at a rate of 48 meters per second squared. Determine the mass. So we know now, and also you can just write this simply as F equals ma, unless you have multiple forces. And then you have to write the summation symbol, sigma. But in this case, of course, you only have one force acting, and you want to determine the mass. So of course, we know that the equation will be that the mass is the force divided by the acceleration. So that doesn't even require you to pull out your calculator hardly. You've got 12 newtons divided by 48. So if we reduce that number, 12 goes into 12 one time, goes into 48, that's 1/4. We take 1/4, of course, write that as a decimal, and we get what? 0.25 kilograms. So that's how we solve that problem. Let's look at number 7. Okay. What does number 7 say? Number 7 says a net force of 25 newtons is applied for 5.7 seconds to a 12 kilogram box initially at rest. So let's identify what is given in this problem. First, we have a net force. So my force is 25 newtons. It is applied for 5.7 seconds. So that's my time. 5.7 seconds. To a 12 kilogram box. That's my mass. My mass is 12 kilograms. Initially at rest, my initial velocity is 0. What is the speed of the box at the end of the 5.7 seconds interval? In other words, what is my final speed? So now, unlike the problem we first solved, this problem has a little more detail. It's asking us to find a little bit more. But like the first problem we just saw, my starting point is F equals MA. But of course, A is not given explicitly. But we already learned in the last chapter that change in speed over time gives me acceleration. So if I know the acceleration, I can find the final speed. So from here, I can solve for the acceleration. So the acceleration then is my force, which is 25 newtons, divided by my mass, which is 12 kilograms. So that gives me 25 over 12, whatever that number is, meters per second squared. So although it wasn't given to me explicitly, I know what my acceleration is. It's always F over M. So even though I don't have it explicitly given, whatever this ratio is, that's my acceleration in units of meters per second squared. So now, because I have already learned my kinematic equations, and I know that acceleration is change in speed over time. Change is V final minus V initial, but V initial is 0, so it's just V final over time. So now V final is my unknown, but I know what A is. So if I have an equation, which I already know from previous times, that V final is just acceleration times time, which is the same thing it was when we used to do the equation before. We had V final is V initial plus AT. This is the same equation. So now we have learned the fundamentals, and we recognize this equation now as the final speed when a force is applied to an object. That object accelerates, and we have the time that accelerates to give me the final speed. So now I can solve for V final. So V final now is acceleration, which is 25 over 12 meters per second squared. And my time is 5.7 seconds. So one of those will cancel out one of those seconds squared. So now in my calculator, I'm going to take 25 divided by 12 to get that answer and multiply it by 5.7. So which one of these is my answer? A, B, C, D, or E? I'll give credit to who give me the answer first. Remember, we're supposed to always have our calculators out when we're in this class. We always have our calculators out so we can work along with the professor and get our answers. Okay, let's see who has the right answer. Okay, very good. Nigel. So when you find that answer on your calculator, you're going to choose B. Is Nigel the only one who can do that simple problem? I would think everybody in the class could do a problem that simple. So I'm thinking that Nigel is the only one paying attention to this class because that problem is so simple. I can't see how anybody would not be able to solve it. You're multiplying 25 times 5.7 and dividing it by 12. But so far, only Nigel can solve such a simple problem. That is not good. I'm inclined to believe that the others of you are not here. Let's see, somebody else has chimed in. Okay. Kaylin, thank you. Okay, Naisha, Nisha, thank you. Anybody else? Monier, thank you. Okay, all right. So the answer is B. You should get 11.8, and for 2 sig figs, that would give you 12. So you would choose B. Very good. Okay, let's go on to another problem. Very good. Okay. Any questions so far before I go on to another problem? Are you all getting the equation F equals ma? And you're seeing under this A is the A that we had in the previous chapters, acceleration. Let's look at problem number 8. Okay, I'm going to erase everything. Okay, problem number 8. I'm going to put the given up here so that I can have space to work it down there. A 975 kilogram, that's my mass. 975 kilograms. Accelerates from rest. That means that my initial velocity is 0. To 26.7, that's my final velocity. 26.7 meters per second. And a distance of, so my distance along the x-axis is 120 meters. What is the magnitude of the force? Okay, so now it wants to know what is force. So of course I know that force is ma. So that means that all of this is given for me to find what A is. Mass is given. So I have an equation that says V final squared is V initial squared plus 2AX. And this is the A that I need. And of course, this implies then that A is V final squared minus V initial squared, but that's 0. Let's ignore that. Over 2x. So the first thing we know is that I can find the acceleration with what is given. But there is no real need to find this number as a number. Of course, you could, but if I were you, I would simply say F equals ma, which is m, and a now is v final squared over 2x. Then I would plug in my numbers. You see, the beauty of physics is that it's almost like writing code or writing, in this case, these are equations. So before I do any intermediate work, I first of all write what I'm looking for in terms of everything I have given. So I have the mass given, I have the final speed given, and I have x given. So now I'm going to plug in my values. So my value is 975 kilograms. My speed is 26.7 meters per second squared. All that's divided by 2 times 120 meters. Now, I want to write this out to show you something, because this will be a good thing going forward. You see, in your calculator, you cannot put in these letters. You're only putting in the numerical values. So that means then that now we begin to learn these equations, we see something here. We see that if I put in my numerical values with the correct SI unit for that quantity, then I'm going to get out a number with the SI unit for the quantity I'm looking for. So when I put in my calculator, 26.7 and square it, multiply that by 975, divide it by 2, and divide it by 120, that will give me a number in newtons. So let me see what your number is. I want to see your number on your calculator before you tell me whether it's A, B, C, or D. Everybody go ahead and put your numbers in. I got 2 so far. Okay, I'm looking for the actual numbers that you see that are in your calculator. So let me go and see. Okay, very good. Okay, Keston chimed in first, followed by Monier, followed by Nigel, Morgan, and Kaylin. Okay, very good. All right. So now, what letter are you going to choose? Of course, you're going to choose what? B, because you have 2896. You're going to round that up into 2 sig figs. 2 sig figs because this number here has only 2 significant digits. This one has 3 and this one has 3, but this one only has 2. And therefore, our answer can only have 2 significant digits. Okay, so let's look at one like number 9. Okay, number 9. All right, let's work on this one together. Okay, number 9. I'm going to write the given up here and solve the problem down below. Mass. Is traveling along a straight level road at a constant speed. So my initial speed is 55 kilometers per hour. When the driver removes his foot from the accelerator, after 21 seconds, that's my time, the truck speed is 33 kilometers per hour. So the speed now has reduced to 33 kilometers per hour. What is the magnitude of the average net force? So now what is force? So we know that force is ma, and in this case, A is going to be what? Change in speed over time. So first we got to solve for this A. So A, of course, is change in speed. So my change, it goes from 55 to 33. So it's getting slower. So of course this is a negative number, but because it only wants the magnitude, I can just give what is the change. So of course it changed by 22 kilometers per hour per 21 seconds. So the first thing we notice, class, is that these are mixed units. So before I can solve this problem, I've got to do what? Convert these kilometers per hour into meters per second. But we've done that several times. So see if you remember how simple that is. Remember that kilometer simply means what? 10 to the what? Third. Or another way to think of that is this. Before I even do that, let me show you this. This is what I want you to think about when you see these numbers. I want you to think about this. An hour, okay? So we have 22 kilometers. An hour is what? 3.6. Remember? Kilosecond. Do you remember us doing that? We said that 1 hour is 3,600 seconds, which is 3.6 kiloseconds. So we have 3.6 kiloseconds per second. Kilo and kilo cancels out. So we're going to have so many meters per second squared. So I hope you recognize now, when you go from kilometers per hour to meters per second, you simply divide by 3.6. That's what you do. You divide by 3.6. So when I do this number, get this value, I've got 22 divide 3.6 divide 21. That's my acceleration. And then I multiply that by my mass, and that'll give me my force. Okay, who can give me the answer first? Okay, I'm looking for the first answer. F equals ma. I want one of my females to be first sometimes. All my guys are first, usually. Sometimes some of the girls are first, but I want you got to work quickly and give me the right answer. Give me your answer. Give me your answer with 5 sig figs first, and then we'll choose one of the A, B, C, D. Give me your answer with 5 sig figs, and then the letter beneath that, what your letter is. A, B, C, D, E. Nobody has it yet? Okay, one person has it. Okay, I'm waiting for the next two. Okay, 2 people have it. I don't know who you are yet. Waiting for the third person to chime in. I'm waiting for the third person to chime in with the answer. Nobody? Only 2? Let's see who those 2 are. Let's see if you have it correct. Okay, those 2 people are, oh, okay. Oops, I'm trying to think. Do I have, okay. Kaylin, are you all answering the first? No, no, no. So far, I don't have the right answer. Okay, so far, I don't have the right answer. Okay, somebody else chime in. Let's see what this person is saying. Okay, okay. I think I like that answer from Nigel. I'm looking for some other answers. Okay, I think only, okay, Nigel has the right answer. Okay, so what we're doing, class, is we're looking for the force. The mass is given here. Acceleration, we have to find it here. So we have 22, but that's in kilometers per hour. So first we divide 22 by 3.6. Once we get that answer, we divide that by 21. And that gives me my acceleration in meters per second per second. Then once I get my acceleration, which I thought was 0.291, that's what I got for the acceleration. Then I multiply that by 2150, and that would give me the force. So let's see what somebody else has. Okay, very good. Now, the reason why your answer would not round up correctly, Kaylin, is because, okay, that's better. That's better. Okay. Okay. That's better, Kaylin. All right. Any questions on this problem? I want to know why the others did not get the right answer. Okay. If you have any questions, you feel free to text me, because I'm about to send all of this to you now. All of this is now your homework. Okay. Work it out on the screen. All right. Let me do that very quickly. $21.50. Okay, let me go to my okay. So in that problem, we were told the mass was 2150 kilograms. Initially, it was moving at 55 kilometers per hour. Okay. Then it slowed down to 33 kilometers per hour in a time of 21 seconds, and was asked to find the force. Of course, the force is mass times acceleration. The acceleration, we know in this case, is the change in speed over time. But we aren't able to just put these numbers in now, simply because these numbers are not the SI units. That's what I pointed out in the previous problem. We cannot just put numbers in unless they are in the SI unit. So the first thing we got to do is find acceleration in the SI units. So we have change in speed, which in this case was 33 minus 55 kilometers per hour divided by 21 seconds. So herein is our first calculation. And because he wanted the magnitude, even though this number is negative, and of course it has to be negative because it's slowing down. We know it has to be a negative number because it's slowing down. However, the units are mixed units. So I showed you in the previous frame, and I'll show you again down here. To go from 22 kilometers per hour to meters per second, you simply divide by 3.6. And where did that 3.6 come from? Well, we have 22 kilometers, kilometers per hour. And an hour is 3.6 kiloseconds. That's what it is. So when these kilos cancel out, my units are now meters per second. So that means then that I simply take this number and divide it first by 3.6 to get my acceleration, to get my speed, change in speed in meters per second, and then divide by 21 to get my acceleration. So when I do this number here, then I still got to divide by the what? The 21 seconds, right? That was my what? That was my time. And therefore, I will get 22, divide 3.6, divide 21. I have meters per second times second, which is meters per second squared, and that'll give me my acceleration. So that's what we have to do first. And when we did that, you should have gotten 0.291 meters per second squared. That's my acceleration. So now I can come back up here, F equals ma. So take this number in my calculator, multiply it by 2150. And now I've got kilogram meter per second squared. Now I have that number in newtons. Does it answer your question? So first I have to find acceleration here. Multiply that by my mass. Then I have my force in newtons. Okay, and the reason why we write this number as a positive number, because the author asks for the magnitude. Magnitude always means it's a positive number. And of course, the fact that it got slower is because it's decelerating. It's getting slower. That's why this number is negative. Okay. So the rest of these problems now are for you to work out. I'm going to send this to you as an assignment. I will not be able to put it in Blackboard. So I just need for you to send me back a sheet. And this sheet is simply your name, okay? I need a sheet with your name, like my name is Edwards, okay? And then 1A, whatever it is, 2, like that. Now, I need you to send this back to me before class tomorrow so I can grade it before I give you the answers. So please send this back to me before, I'll say by 1 o'clock on tomorrow. Your name and then the answer. That's all I need. I think you have 22 problems to solve. So I'm going to send this to you now, and this is your assignment. Okay, time is up. Please sign your name as you exit. You can sign your name as you exit.
Dr. Edwards,
Yes, sir.